Hello, everyone. Welcome to the Dr. J Vlog series. It is Monday, January 20th, 2025. You know what that means? Just a Mathematics Monday. That's right. On Mondays, we deal with mathematics and statistics, everyone's favorite subject. Well, today I thought we'd do something a bit different. You probably recall we had the pandemic a few years back, and during the pandemic, we had the university shut down, in-person classes, and we were just teaching everything online. So I thought I would share with you an example of my online teaching. And I was teaching intro statistics that particular semester. I do teach introduction to statistics and advanced statistics, that sort of thing at the university level. And I thought I would try this out to see if you enjoy this type of learning. And if you do, well, I'm thinking about posting the entire course online, basically an introduction to statistics. So, what I'm sharing today with you, what I've done is I've recorded this little intro and then we spliced it together with the original lecture that I delivered almost 4 years ago to the day. It was January 2021. So it's a bit long, it's a bit lengthy. I don't expect you to sit through the entire thing unless you love to learn about statistics and more specifically about the normal curve and probability distributions. It's a great set of tools to have in your arsenal, something to think about. And if you want to learn more, just let me know in the comments. All right, without further ado, let's dive into statistics.
Hello, everyone. Welcome to A Late Show. I'm your host, Stephen Colbert. Oh, sorry, wrong show. No, this is statistics, right? Anyway, and today is actually Thursday, January 28th, not the 29th, as it says there on your screen. I'm recording this a day early because today is Bell's Let's Talk Day. So I thought we could talk about statistics and mental health issues and dating and relationships and so forth. But anyway, I wanted to share with you my mental health companion. This is Maverick. Maverick, can you say hello to everybody? Maverick? Maverick? Say hello? Hi? No? Well, he's waving. I guess that counts for something. Anyway, this is Maverick. Maverick is a is my little kitty. Uh, I went to. I'm a dog person historically, right? So that's my sort of prejudice, if you will. And but I went to the vet one day with one of our dogs about 10 years ago, and they had four little kittens there, and one of the kittens was really tiny, the runt of the litter, as they say. And I asked the vet about that. They said, "Oh yeah, they're giving the cats away for free. They'd all been, vaccinated and neutered, I guess, and so on." But anyway, um, I said, "Oh, that's interesting." And I said, "Can I pick one up?" She said, "Sure." So I went to the little runt, and as soon as I picked him up, he just started purring like crazy. He was so happy. She said, "Oh yeah, he wasn't supposed to live, but he'd survived." So I just kind of fell in love with him right there on the spot. And yeah, I brought him home. My wife was shocked because she's more of a cat person, you know. So anyway, I know it's end times, biblical, and all that. We had cats and dogs living together and everything else. But anyway, yeah. So that's where uh, Maverick came from, and now he's my big 17-pound fluffy cat. He's not the runt of the litter anymore. Okay. And of course, I'm not much of a runt anymore either. We all put on a little bit of weight over the years. So anyway, yeah. So he's my buddy, and he still purrs like crazy. And I'm gonna try and get rid of him now if I can. But well, now he's up on well he's up on the desk. He's walking around. He's sniffing. He's doing his thing. He's getting hair all over my computer. I literally have to get rid of the hair now. Anyway, um, so I'm just showing you that I do, in fact, exist. I assume that you exist. If you're watching this video, I'll presume that you are in existence. You're an existing human being at the moment. And I hope you're doing well. And I hope you're taking care of yourselves. I hope you're taking care of each other, as our principal likes to say, and finding the love and the support and everything that you need to cope and not just to survive, but hopefully to even thrive under these rather difficult circumstances. Okay. So without further ado, we shall get now into the discussion of today, which is the normal curve, z-scores, and estimating probabilities. And if you don't mind, I'll shut off the video because you really don't want to look at my ugly face the whole time. It's a bit of a distraction. All right. Anyway, hope you're doing well, and let's get on with the show. Okay, so we'd mentioned the normal curve previously, but I really didn't go into any depth or discussion about the normal curve. But it's incredibly important, and you'll see why over the remainder of the course. But we'll get you started on that today. But it's an especially important feature of what we call inferential statistics. So there are two overarching main branches of statistics: descriptive, which is what we've been looking at the first couple of weeks, and inferential statistics. So inferential, from the term inference, means we're trying to make an inference or an estimate of a broader population based on sample statistics. Okay, so the whole branch of inferential statistics implies that we are not studying an entire population, but rather we're studying some kind of a sample, ideally a random or probability sample of cases from a general population. And then when we do our analyses, we want to know whether or not the statistical relationships that we observe can be applied or apply with a certain degree of accuracy to a more general population. So that's the whole branch of inferential statistics. And we need the normal curve in order to be able to make inferences about the general population. The normal curve allows us then not only to come up with descriptive counts and estimates, but we can also look at the degree of randomness and the degree of heterogeneity across a population based on our knowledge of what we expect to find in the normal population. And so we actually use the adjective normal to describe the curve, both because of its geometric properties as well as its other mathematical properties. Okay, so that's what we're going to be looking at today, and we're going to look at how this so-called normal curve allows us then to make inferences about more general populations. What you see in front of you there is just a nondescript normal curve, that bell-shaped distribution that's plotted on a graph. The x-axis, as it's typically described, shows the spread of the distribution, and then the y-axis is now actually defined by f, or the frequency of the occurrences and the number of cases. And what we say very simply is that the normal curve can be plotted as a simple frequency polygon. But of course, it has very special properties as a polygon, as a frequency polygon. Among other things, we know that it's, as I mentioned, bell-shaped. Okay, you see the distribution there. It's also unimodal. There's only one mode, so if you go to the absolute peak of the distribution, that's the highest point, and that also represents the greatest frequency, right? The most common number of cases, so it's right there at the tip of the distribution. You'll also notice that it's symmetrical along the abscissa, the x-axis there, right? So the distribution is, we could say, mirrors each other on either side of that peak in the distribution. It's also asymptotic, which means that those tails don't actually touch the axis, but they extend into infinity. And you'll see why that is mathematically in a few minutes. You'll also note that not only is it unimodal, but the mean, the median, and the mode all occur exactly at that same peak, right there in the middle of that distribution. Well, the median, of course, by definition, has to be the midpoint of a distribution. But that figure, whatever the mean is on this hypothetical frequency polygon. It's also, whatever the median happens to be, that center point, it also happens to be the mean, right? Because it's symmetrical bell-shaped curve. So as I say, it's mirroring each other on either side. And the mode as well. All of those then can be found right there at that theoretical peak of that distribution. Okay? And this is quite important. It's a theoretical model, an ideal model, right? It's not real in the sense that it represents the reality itself. It's used as a theoretical descriptor of an imagined reality, an imagined distribution. We don't necessarily know what the real distributions are of different traits or characteristics or things like attitudes and so forth are in the population. We're trying to estimate those things. We're trying to make some informed judgments based on gathering evidence, gathering data, and then examining that data. But when we do that against the backdrop of theoretically what do we imagine or what should a normal distribution or of a population, what should it look like? Okay, this is an important distinction too, because as you might guess or imagine, not all characteristics and traits and attitudes and incomes and things that we might want to measure, not everything's going to have necessarily an absolutely normal distribution within the population, whatever that theoretical population might be. But many things do. And what we're doing with a lot of our inferential statistics, and at least to the extent that we base them on the normal curve, and this isn't the only, by the way, this is what we're going to be using mostly in this course. It isn't the only curve that we use, and it isn't the only kind of theoretical model that we can use. Okay, but you have to start somewhere in statistics. So we're starting with the basics, with the foundations. We're starting with the normal curve. And a lot of what we'll be studying, a lot of the kinds of things that we're interested in studying in sociology, do in fact approximate normal distributions within general populations. And so it's appropriate for us to be able to use this model, again, with some caveats and some restrictions, and we'll note those as we go along in the course. Okay? All right, so that's your introduction to what this actually looks like and some of the key characteristics. What else do we want to say about this normal curve? In other words, what's so special about being normal? Well, as I just mentioned, a lot of the variables that we may be interested in, but again, not all, have distributions that tend to approximate the normal curve. Okay, so for example, we could look at everybody's age in this classroom, right? And we could imagine that that were our total population. That everybody who attended King's was attending this class in statistics. So King's would be a very small college then, right, with only 55, 60 students. So, but imagine that everybody, the entire population of King's was attending this particular statistics course. What we could then do is go around and measure everybody's age. Probably just ask you your age. Don't mean to be rude, but we, we could ask for your ages. And then we could gather that data and we could enter it into an Excel spreadsheet or into some kind of a statistical program. And then we could generate a curve. And guess what we'd find? In all likelihood, we'd find a relatively normal distribution with everybody's, with the mean, the median, and the mode, again, at the peak of that distribution. And what we'd probably find is that the average age in the amongst all of you, and in fact, if we were in class, we could actually do this very quickly, right? But again, we're doing this online, so we don't quite have that luxury. But we could go around, get everybody's age, okay, as I say, enter it in, compute, and then compute the mean, the median, and the mode. And the chances are we'd find that there'd be something like the mean, the median, and mode would probably all be somewhere around 21 years of age. Again, some of you are going to be older, some are going to be younger, some of you are going to be exactly 21, and so on, right? And then you're going to have some what we call outliers, some people that are a little bit further above the curve or perhaps even below the curve. We had somebody actually at King's, this is actually true, a couple of years ago, who came from Ghana. She was a young woman, and she entered King's, right, in first year as a 14-year-old, right? Hard to believe. At 14, I was in ninth grade, and I don't know, I was doing geometry, and who knows what I was doing, just being an idiot probably. But anyway, she was she entered first year university, first year at King's as a 14-year-old, so obviously quite bright. Um, but yeah, so we're going to find the odd outlier, the person who's a little bit older. Sometimes the oldest person, this is kind of fun, the oldest person I've ever taught or had in a class, this occurred when I was teaching at Trent University in Peterborough. So this is, oh gosh, over 20 years ago now. But I had a woman who was, she'd taught kindergarten and all her life, but she came back to finish her degree. And my course was the last course she was taking. She was 74 years old, and she had to pass my course, and she got her degree after she passed. By the way, she just barely passed my course, unfortunately. It was a bit of a struggle for her, but to her credit, she hung in there and she did pass and she got her degree at age 74. So that's the oldest student I've taught in university. All right, let's move on though. So in addition, if the point is that if the variable distributions that we're looking at are or can at least approximate the normal curve, then there are a number of mathematical properties that are important and that apply. And you can imagine why that would be just looking at the curve itself, right? But most importantly for our purposes, what that would indicate is that we can readily calculate the means, which you already know how to do, and we can calculate the standard deviations. Again, something that you already know how to do. And these are two of the most important statistics that we use, that are commonly used, and often serve as the basis for all kinds of other analyses. But most importantly today, what we can then do with this information is we can then look at and estimate or look at what the proportion is or the percentages of cases within that normal curve, how they're distributed, and the likelihood of anybody falling within a certain range or within a certain area under that normal curve. So it's almost like doing calculus, but of course we're not going to do anything nearly as complex mathematically as calculus. But the point is that we're going to be able to use the information based on the normal curve to make some really interesting estimates about the characteristics of who or whatever it is that we're studying. Okay, so I'm going to show you how to do that in just a moment. So here's the bell curve, right? And Bell, as you know, is sponsoring Let's Talk. So let's talk, and it is today. Today is the day, January 28th. So let's talk. But instead of mental health issues today, we're going to focus mainly on the bell curve. All right. So let's talk about that. You'll see some interesting markings and some mathematical operators there, or statements. That should look a lot like gobbledygook at this point. But what I'll simply say to kick things off is that if you look at the absolute middle of that normal curve, the center of that bell curve, and you go to the peak, right? What did I say about the peak? The mean, the median, and the mode all occur and all are represented by the exact same figure on a given distribution, right there at the peak of that curve, of that normal curve. What that normal curve also represents is a distribution of cases, right, or a sample of individuals, or their income levels, or their ages, or whatever it may be that we're, as I say, that we're studying, okay? And around the middle of that curve, look at the area under the curve. So look at right immediately on to the right and the left of the center of that curve, that center line. And you'll see the figure's 34.1%. What that represents geometrically, is the area, the percentage of the area actually that's filled in under the curve in that zone. Okay, so you see the center line, and then you see a black line to the right, a black line to the left. And that area that's actually colored in there, what would you call it? Kind of like a light blue, a very light blue or light bluish gray. That area under the normal curve represents 34.1%. That one area to the right of that line, center line, as well as as I said, it's a mirror, the area to the left of that center line. All right. And if you combine that together, then it's 34.13. Like there's the hundreds and thousands go on forever. But if you combine that, you're talking about the two areas combined represent about 68.3%, just over 2/3 of the total area under the curve. What that means is that that's where 2/3 of the cases, 68%, 68.3% of the cases of the normal distribution lie. That is to say, if we were looking at our class ages, if the mean, the median, and the mode, if it were a totally normal distribution, were 21, we'd expect 68% of the people to be within a certain range of 21. All right. And that depends on literally something called the standard deviation. So how widely distributed, how spread out are the ages, or how much are they clustered together? If you had a class of all 21-year-olds, there would be literally no deviation, right? Everybody would be 21 by definition. We've just said that, right? And so instead of a normal curve, you just have one vertical line that extends to the peak and however many cases there are, how many students there are in the class, and that would be it. There wouldn't be any spread about that line. But of course, what do we expect to find? Not only 21-year-olds, but we expect to find 20-year-olds and 19-year-olds and 22-year-olds and 23-year-olds and so on, right? So the point is that around that center line of the 21-year-olds, we'd expect to find about 68% of the class should be within a certain range of that middle point of the distribution. Should be pretty close to 21, okay? And then the further away you get from that line, the further you get away from 21-year-olds. So if you go to the right of the curve, you're going to be talking about people that are at least what's called a standard deviation above 21, and maybe more, right? To some theoretical limit, whatever that might be. I guess somebody could be, 115. Not likely, but that's certainly possible. And as I mentioned, we had a 14-year-old here at King. So in principle, we could have potentially like a 14 or a 15-year-old second year class. Maybe we could have a 15-year-old in the class as well. But those are unusual, right? But what do you see happening? Instead, most people, quote unquote, are normal, or they cluster towards the center of the distribution. All right. So we'll talk about these figures and what they mean, what they represent, but I just wanted to give you a brief intro and a visual that I'd like you to sort of bear in mind as we move forward. So the example that I've created to illustrate exactly what it is we're talking about is a distribution of males and females. Okay, so I've actually separated them out. And in particular, what I've done is I've created an imaginary pair of distributions measuring the grades of the males and the grades of the females. Okay, now in this particular statistical sample, you'll notice that the average grade, that's the X bar. You see that? The X bar for both distributions, males and females, the average grade is, the mean is 70. Okay, so imagine we gave a test, or maybe this is their end of year marks, whatever the case may be, but imagine that we gave a test, and so the average for the males in the class was 70, the average for the females was 70. All right, simple enough. All right, in addition, you'll notice that not only do they have, well, on the one hand, they have the same mean, the same average. On the other hand, you can see that the distributions look markedly different, don't they? Clearly, the females' distribution is more spread out compared to the males. And what that means is that the average deviation, or in particular the standard deviation for the females, has increased relative to the males. And as that standard deviation spreads out, in other words, as you get more dispersion about the mean, more people with high scores, more people with low scores, the curve, the shape of the curve changes and it becomes flatter. Okay? So even if you don't know exactly what the mathematical results are, again, you're given the means in both cases, but the S is the standard deviation, and you'll see that it's 10 on the left for males and 25 for females. So that statistical information tells you that the females have a much wider distribution, much more variability in their test scores compared to the males, who tend to cluster more closely together about that mean of 70. Even if I didn't give you the X bar and the S's, that is the mean and the standard deviations, just by looking at the graphs, assuming that they were scaled the same way, using the same metrics, the same measurement metrics, right? You could tell that the females have a more spread out distribution as opposed to the greater centralization and clustering amongst the males. So these are critically important statistics then that we want to use to be able to characterize what's happening with respect to the test. And there's all kinds of interesting things then that we can say about the testing scores and the results between males and females on the basis of this information. Where we want to start then is to talk about something that's often called the empirical rule. And this is what I was hinting at when I showed you the normal distribution a couple of slides ago. But in any given normal distribution, the empirical rule applies, so that if you look at the mean of the distribution, the X bar, plus or minus one standard deviation, is going to capture 68.26% of the cases in that distribution. Go back 2 slides and you'll see what I'm talking about. That is to say, you're going to capture just over 2/3 of all of the cases in the sample on either side of the middle of and the mean of that distribution. Okay? By definition, that's true. And if you were to do calculus, the area under the curve literally represents 68.26%. If you calculate a mean and a standard deviation and you take plus or minus one standard deviation on either side of that mean, you're going to find that that covers 68.26% of the area under the curve, which represents 68.26% of the cases in your sample. Similarly, if you take that same mean, it's the same distribution, and you add or subtract 2 standard deviations, you'll capture the vast majority of all the cases within the sample, over 95%. And then within 3 standard deviations of the mean on either side, you're going to capture almost all of the area under the curve, 99.72% in fact of the cases. So this is incredibly important, and it's a statistical and a geometric property and a calculus statistic that represents area under the curve, which translates into the numbers of cases that we've captured, and that logically and empirically should lie within a range of the mean. Okay, so again, if a variable is distributed normally, then just over 68% of the cases are going to lie within one or plus or minus 1 standard deviation of the mean. Similarly, roughly 95% of the cases are going to lie within 2 standard deviations of the mean. And then, as I've mentioned, over 99% of the cases are going to lie within plus or minus 3 standard deviations of the mean. So to be beyond that, you'd really have to be unusual. You'd really have to be an outlier. Okay? And we'll talk about those as well. Here I've provided another empirical rule illustration, and you see the normal curve. You'll see the figures that I've broken them down. Excuse me, around that mu, that middle figure, that's the Greek letter mu, which refers to the population mean. I'll just, again, introduce a little bit more terminology here. The X bar is the mean of your statistical sample. What we're trying to estimate, though, is whether or not the statistical sample applies to a more general population. Mu is the statistical mean for the entire population. All right, so X bar is the mean of the sample. Mu would be, if you can imagine, if we captured everybody in a population, then that's what mu represents. So mu in this case represents the standard deviation of the normal distribution that's found within a population as a whole. Once more, what we observe then is that about 68% of all the cases in a normally distributed set of cases in a population should fall within plus or minus 1 standard deviation. And you'll see there we've shifted again from the statistical, from the S for the standard deviation, and we've instead included a Greek symbol there as well. Okay, so now we've got the mu plus or minus 1 standard deviation for the population as a whole. Okay, and then again we see what the distribution looks like if we were to capture plus or minus 2 standard deviations in the population as a whole. And then finally, you'll see that within plus or minus 3 standard deviations, we capture nearly all of the cases within the distribution. You see that the tail, again, does extend further, but we've cut it off there at plus or minus 3 standard deviations of the mean. And there's a tiny bit of curve beyond that, right? So there's a few cases that lie even further to the left and to the right, or above and below whatever mean it is that we've calculated there. Okay, so let's go back to our example where we gave the students a test, and we looked at the distribution of the results for males and females. And if they're normally distributed, what we can then say, of course, is that roughly 68.26% of the males should have grades close to 70. How close? They should be within plus or minus one standard deviation of the mean. So if the mean is 70, plus or minus one standard, and the standard deviation is 10, plus or minus, that's what gives us this range from 60 to 80. You see that? We do the simple math. So 70 would be the mean for the males, minus one standard deviation would be 60, plus one standard deviation would be 80. And what that suggests then is that over two-thirds, about 68% of the males should have grades, should have scored between 60 and 80 on this particular test. Okay. Similarly, for females, we notice that there's a much broader spread, a much broader distribution. Their mean is still 70, but unlike the males, their standard deviation is 25. So if you do 70, the mean plus 25, that's going to give you 95. 70 minus 25 is going to give you 45. So unlike the males, about 68% of the females have grades between 45 and 95, plus or minus one standard deviation of the mean. Do you see that? Does that make sense? Again, it indicates both visually but also mathematically that the scores for the females were much more spread out. We would say that they're more heterogeneous, they're more diverse, right? And there's a higher and lower number of more extreme cases as compared with the males.
All right. I think we'll stop there for today. I think that's enough mathematics. And I have another kitty cat who wants to say goodbye now. We've switched from Maverick to Lucy. Go figure. I'm not even a cat person. But anyway, hopefully you'll join us again for some more mathematics and statistics and some other fun stuff another Monday. But for now, may you and yours continue to create peace in your lives and nurture love in your hearts. And we'll see you soon. Bye bye.